So, our last topic for the semester is Newtonian gravity. And I posted a PDF and YouTube lesson for you on Newtonian gravity. And I posted information about it on Blackboard under the remote lecture materials area. But I thought I'd start out today by giving a really quick overview. I'm not going to go through as many details as I did before. So on Earth, we know we calculate gravity, the force of gravity, as just the mass of our object times this constant g. And we know the direction is downwards. So we could add that to the description as like part of the vector meaning. In general, we need a formula for gravity that takes into account the fact that the force of gravity gets weaker when you get further away from the planet. And also, the force of gravity depends on what planet you're near. So I call this F sub capital G, whoops, F sub capital G, and it's equal to the constant capital G times 2 masses over r squared. So I need to define what these things are. The constant capital G is on the equation sheet, but it's 6.67 times 10 to the minus 11th. The capital M is the planet mass, and R is the center to center distance. So we're still trying to calculate the force of gravity affecting our object, but now it depends on more things than just the mass of our object. It also depends on the distance our object is from the nearby planet and the amount of mass in the nearby planet. If we're talking about Earth, then the mass of Earth is 5.97 times 10 to the 24th kilograms. It's a lot of kilograms. And the center to center distance when you're actually on the surface of Earth is called the radius of Earth, because the size of your object doesn't really matter when you're talking about 6371 kilometers. And that's the number I put on the equation sheet for the radius of Earth. Earth isn't really perfectly round, so depending on exactly how you measure it and how you describe it, the radius is somewhat variable. Now, when we do energy analysis on Earth, we get to do an easy version of U sub G is minus the integral of the force of gravity, which is minus F sub G times dy on the inside. And that turns into mgy plus c. And the way we get rid of the plus c so we don't have to deal with it is we just say, well, we can set y equals 0 wherever we want. So we'll just set c equals 0 and set y equals 0 at maybe the floor of the laboratory or the tabletop or whatever point is convenient for our analysis. So y is height above origin of coordinate system. Now that's different from the r value from the Newtonian gravity formula. The r value is your distance from the center of the planet, not from the origin of your user-chosen coordinate system. So that's a big difference. And when we go to calculate the potential energy due to Newtonian gravity, capital G, it is minus the integral of minus, I'm actually going to put it in here, G m m over r squared dr. So there's a lot of minus signs to take into account. There's one that's part of the definition of a potential energy function, that when you move in the direction of the force, it does work on you, but when you move in the opposite direction, you're doing work on it. So it's actually absorbing energy. And then there's a minus sign that's because this force is an attractive force. And then we have to do the integral of this. Now the GMM is still there. Those are constants as far as this integral is concerned. Now we have to do the integral of 1 over r squared. And of course, you know that like to integrate x squared, it turns into x cubed over 3. So you raise the power by 1 and then divide by the new power. So we have to take this power, which is a minus 2 power, raise it by 1, so it becomes a minus 1 power. So it's planar now. And then divide by the power, divide by minus 1, puts in a minus sign. And we set C, we have to include the plus C there. And over here with regular gravity, we just say C equals 0. And we don't care what the value of C is, because every time we actually deal with potential energy, we're comparing two locations. We're comparing the potential energy at a height versus the potential energy at the ground. And if you add a plus C to one of them, you have to do it to both of them. So who cares if you add the plus C? Here, we're also going to kill the plus C and move that down a little bit. Note over here, UG equals 0, where y equals 0. Because if you get rid of that, UG is mgy, you set y equals 0, and your potential energy due to regular gravity is 0. Over here, U capital G equals 0, where r equals, what do we have to do to r to make this whole fraction go to 0? We just have to make it bigger and bigger and bigger, as big as possible. So we say that's where r equals infinity. So those are the two important formulas of Newtonian gravity: the force due to gravity right here, and the potential energy due to gravity here. Oh, we have one more thing to worry about, and that is the idea of an orbit. And with an orbit, we basically have our planet. So I'm going to try to draw the Earth. There is a wonderful circle. Now I'm going to try to draw something to represent that this actually is Earth. There we go. I think that looks like Earth, and that's almost as good as I'm ever going to do. And we put a little dot on there. Now we'll put a dot on there to represent where we are. So we have this thing up here, which is moving along with a velocity v. And as it moves, it gets attracted to Earth. And if things are just right, then it will end up going in circle. So if we do a force diagram of our mass, then its only force is the force of gravity. So then we can say the force of gravity is equal to A, and we can take the magnitude of both sides and end up saying that G m m over r squared is equal to mv squared over r. And that's basically what we do for most Newtonian most Newtonian gravity orbit analyses. And another way to think of this is to cancel out the r's and move and cancel out the little m's, and you get g m over r is equal to v squared. So there's one more thing we tend to put in here, and that is that for one orbit, the distance is equal to 2 pi r. The time is a special amount of time we call the period, capital T. So then v, the speed, is 2 pi r over capital T. So we can plug that in here. We get g m over r is 2 pi r over capital T, quantity squared. And then let's cross multiply and get rid of all the fractions, and we get g m capital T squared equals 4 pi squared r cubed. And this, by the way, is called Kepler's third law. It says for objects orbiting the same planet, the period squared of their orbit is proportional to the radius cubed of the orbit. And I think it's neat how we can put together Newtonian gravity and our idea of circular motion and our basic idea of the definition of speed and come up with Kepler's third law and see that Newtonian gravity and Kepler's laws are really just different ways of manipulating the same information in the same situation. So I want to do an example, and there are some examples in the lecture notes that I posted involving the International Space Station. So I'll let those examples speak for themselves. I think they're very useful in understanding what's going on. Today's example is I'm going to launch a projectile straight up at 5 kilometers per second. And I want to know how high will it go. So first of all, I want to calculate my acceleration. It's not that I need my acceleration, it's just that it's a useful value to calculate. So I'm going to go ahead and figure it out. So with regular gravity, a regular gravity is G. With Newtonian gravity, a capital G is, we figured it out up here. The A is this stuff, the V squared over R. which is this stuff. Basically, the force formula without the little m in it is the acceleration. So let's calculate that. Bm over r squared is 6.67 times 10 to the minus 11th times 5.97 times 10 to the 24th divided by, and I don't know if you knew this, but you can do 6371 times 10 to the third. You can account for the kilometers by just putting a times 10 to the third in there, and then the radius has to be squared. And if you do all that, you get 9.81 meters per second squared. So with regular gravity, your g is 9.8 meters per second squared. And we find out that these two methods agree at the surface. In fact, the 9.81 value is typically the value we use in physics classes if we want a little bit more detail than just rounding it off to 9.8. But if we're going to find the max height, we need to do energy analysis. Now with regular gravity, we can just say that K initial is equal, well, K initial plus U initial is equal to K final plus U final. We don't have any work due to a non-conservative force, so we don't have to worry about that. And we say U is 0 at the surface, K is 0 at the top, and we end up with 1/2 mv initial squared is mgy final. And we cross out the m's, and we find out that y final is v initial squared over 2g. So then I go over to my calculator and I calculate 5,000 squared over 2 times 9.8 to get my max height calculated by the wrong method. So that would be 5,000 squared divided by 2 times 9.8 is, that's a lot, 1.276 times 10 to the 6th meters. That's 1276 kilometers is y final by that method. Now, if we're going to do it by the Newtonian gravity method, we still have K initial plus U initial equals K final plus U final. We can't set either one of these potential energies equal to 0 because potential energy is 0 when R is equal to infinity. Well, we're not dealing with R equals infinity. We're dealing with other values of R. So we're going to have to go 1/2 mv initial squared plus negative g m m over R initial. The potential energy function does not have the R squared in the bottom. And then the K final is equal to 0. So then we're going to have minus G M M over R final. So now let's cancel out the little m's because they're in every term in our equation. So we're going to have 1/2 times 5,000 squared minus 6.67 times 10 to the minus 11th times 5.97 times 10 to the 24th over 6371 times 10 to the third equals minus GM over R final. Let's leave that like that on the right-hand side because I can't do anything about it yet anyway. So now I'm going to boil these two things down into numbers. 0.5 times 5,000 squared 12.5 times 10 to the sixth, and then 6.67 times 10 to the negative 11th times 5.97 times, well, not, yeah, times 10 to the 24th divided by 6371 times 10 to the third, not 10 to the sixth because I already have 6,371 and not squared. And this is minus 62.5 times 10 to the sixth equals minus G M over R. So now I can take my 62.5 minus 12.5 and get 50 times 10 to the sixth is equal to minus G M over R final. And my R final is equal to minus 6.67 times 10 to the minus 11th, 5.97 times 10 to the 24th, all over 50 times 10 to the sixth. And this was a negative, so this turns positive. Six point 67 times 10 to the negative 11th, 5.97 times 10 to the 24th divided by 50 times 10 to the sixth is equal to 7.964 times 10 to the sixth meters is 7964 kilometers. And the height is R final minus R initial is 7964 minus 6371 is equal to 395 and then 1. Yes. So the height that we predicted using Newtonian gravity is actually more. And that's because the force is getting weaker and weaker as you get further away, so your object gets to go further. Let's calculate the A final. That is GM over R final squared. That's everything in the force of gravity formula except for the little m. So gm over 7.964 times 10 to the 6th. Hey, I still have that number in my calculator. So now I can do 6.67 times 10 to the minus 11th times 5.97 times 10 to the 24th divided by answer squared equals 6.28. So the value of G at this very high altitude of 15, well, almost 1,600 kilometers is a lot smaller. And that is why the satellite, well, the projectile gets further by this method. So that's an overview of at least one part of Newtonian gravity calculations and example of orbit using the space shuttle, not space shuttle, the International Space Station as an example is in the lecture notes and videos posted in the remote lecture materials area of Blackboard.